A lot of the mathematical modeling that we do ends up involving trigonometric functions in one form or another. So of course we need to figure out how to take the derivatives of trigonometric functions. So what we want to do in these next several videos here is I want to be able to find the derivative of both sine and cosine functions. These two are biggies. The reason for that is once we know the derivatives of sine and cosine, as you know, all the other trigonometric functions are functions of sine and cosine. So we should be able to use the quotient rule to find the derivatives of the other four trigonometric functions. So before we jump into that, let's talk about a couple of special limits. Now, I'm not going to prove these special limits. There's probably a proof in your book somewhere, and actually we'll come back and prove these when we move on a little bit further and learn what's called L'Hopital's rule, and then the proof for these becomes extremely simplistic and straightforward. The proof in your book, if it's in there, is probably going to be more geometric and a little bit more confusing. So the first one is the limit as x goes to 0 of sine x over x equals 1. Now as x goes to 0, this goes to 0 over 0, which we know is an indeterminate form, so it needs a little bit more work. And what the limit actually turns out to being is 1. Now this is a limit that you can use without proof. Just trust it, use it. If you ever need this limit or a form of this, then you can use this result. The second result is important to know is limit as x goes to 0 of cosine of 0 minus 1 over x is 0. Now again, as x goes to 0, cosine is 1. 1 minus 1 is 0. This is another situation where I have 0 over 0. But the limit as x goes to 0 ends up being 0. Again, when we hit L'Hopital's rule, I'll go over a nice simplistic, very pretty proof of these two. So just as a quick example, I want to use these ideas to find this limit. What's the limit as x approaches 0 of sine of pi x over x? Well, if you notice, this is not sine x over x. This is slightly different. So what I'm going to do is, if I had a pi down here, then it would look a lot more like this. So that's what I'm going to do. I'm going to put a pi there because I need it, but I can't just stick it there because I need it, but I can put a pi out here. So what I just did is I multiplied this by 1. I multiplied by pi over pi. One of the pi stayed out here, and the other pi went inside the limit. It's a constant. Remember, pi is a constant, so the constant can be moved in and out of the limit at will. So now that I have that, I now have something that looks like this. Pi times the limit as x goes to 0 of sine of pi x divided by pi x. Well, this looks an awful lot like this, but not quite. So I'm going to make a substitution here. I'm going to say let theta equal pi x. And notice, as x goes to 0, pi x goes to 0, and obviously theta goes to 0. So when I do that, I end up with, let me come over here, the limit, oh, I need a pi out here, as theta goes to 0 of sine of theta over theta. Now this is exactly like this. It's just my variable is now theta. So this will be equal to pi times 1 because this limit is 1. So therefore, the limit as x goes to 0 of sine of pi x, whoops, put the paren in the wrong spot, sorry about that, sine of pi x divided by x is actually equal to pi.